Good, good afternoon. Good beginning of the evening, almost. All of you, welcome to episode 2 of the first season of Physics 610. Second season, as I was saying, is going to be around the beginning of spring break. Couple of logistical things. The first is that I'm going to be moving my office hours. I really don't like it before class. And I know a lot of you hang out after class anyway, so I'm going to just put it 1 hour after class. But I ask you to, if you need to show up to office hours, to actually show up at the beginning, such that if at some point there are no more questions, I can actually turn this thing off and retire for the evening. Don't show up at 7:29 with 1 minute to go with 50,000 questions. So that's the first thing. If that schedule doesn't work for you, just let me know. I'm my schedule is pretty open. Just shoot me a message and we can jump on something else. But just 3:30 is just not a good time for me. I don't know what I was thinking. Other question. There was let me see. Oh yeah, I had a mistake in my lecture when I was doing the time reversal symmetry. I was going in the right way, but I messed up the E sign, and then afterwards I looked at my notes and then saw that I also afterwards messed up the B sign. So I fixed that. I actually re-recorded that section, and I put it and I inserted it, spliced it like a professional video editor. I spliced it in the video. So the one that you see on box is the one that is the updated one with the corrected sign for the time reversal symmetry, and it's also the one that has the corrected notes. And then I also changed the notes. So if you downloaded it on box, I believe I had for a short period of time, I had the old version up there, but now the new version should be up there, so that should all be good. I try not to make those mistakes too often. First of all, because I think that's not fair to you, but second of all, it's a lot of work to go in and edit videos and splice in things. I would prefer for it to be neatly packed up. So I really try to do my best, but if I see massive errors like that, I can't let it go. So I'll clean it up, I promise. And if you see something during class, feel free to speak up, of course. Then one more thing. There was, forgive me, I forgot the name, but one of the students actually had an excellent question. I was making the point during class that Noether's theorem says that if you have some kind of a symmetry, that there's usually a conserved quantity that is associated with it. But I also talked about the time reversal symmetry and mirror symmetry, and then of course the natural question is, well, what's the conserved quantity? So I should be a little bit more careful. So Noether's theorem only talks about differential symmetries. So symmetries, let's say translational symmetry, right? So you can take a dx in one direction and a dz in another direction, and you can continuously move your system from one state to another. So it's a differential symmetry. For those kind of symmetries, Noether's theorem says that there's a conserved quantity. For things like mirror symmetry, because it's not a differential thing, right? It's a discrete thing. You just flip everything from one side to the other. Noether's theorem doesn't say anything about it. And as far as I can tell, I don't know if there's a conserved quantity that is associated with it, but certainly Noether's theorem has no bearing on it. Okay, so those things out of the way. Let's talk about the material that we'll talk about today. So we have, I had allocated three classes for going through chapter 2, but I think we can actually do it in 2 because I am assuming most of the material is familiar to you. We'll go over a couple of things that you might have not seen before. But there are also some things that are mentioned, but only in passing, and I don't think we need it. So, for instance, one of them is Cauchy's principal value argument and contour integration. There's only 2 places in the book that it's used. One is in the introduction, and one is in chapter 19. And we're going to skip over chapter 19, so I'm going to blow past that. Another thing is that you might have not seen tensors before, and therefore you might have also not seen Einstein notation. So I'll try to do a really good job of explaining it to you, but it is something that usually does take some getting used to. And then I should mention that this book is actually, it's a little heavy on thinking through concepts based on an underlying coordinate system. and especially in the beginning, we're using Cartesian coordinate systems a lot. And unfortunately, there are a lot of bad habits that you or me also, that you will develop if you always stick to thinking about geometrical objects and fields in terms of an underlying Cartesian coordinate system. First of all, it's physically not accurate, right? Because coordinate systems are just a way for us to label how we organize the way we look at space, you know. But like one of my favorite sayings, the electrons don't care, right? So they don't care whether you're using spherical coordinates or Cartesian coordinates. It just sees that there's a field and it goes that way. And unfortunately, many things are defined using the Cartesian coordinate system, and this book actually does that too. So, for instance, famous thing, the dot product, right? So you have two Cartesian vectors, dot product, A and B. Dot product is just AX, BX plus, etc. But that only works in the Cartesian coordinate system. But actually, the dot product actually has a very, very, very important geometric meaning that goes beyond the fact that there's an underlying coordinate system, because it's a projection of one vector onto another. So just forgive me. I'm going to follow the book, but I know that's from a pedagogical point of view, it's not ideal, but we have to take some shortcuts. Similarly speaking, Green's and Stokes theorems are actually special cases of what was his name? I'm blanking on the name. Something from differential geometry, but of course, that's higher math, so we're going to blow past that as well. Another thing that we'll probably get into later, and that is that certain things make sense to define because they have properties that don't change if you change the underlying coordinate system. Such things are invariants, and if you use tensor notation, you'll start throwing indices around, and it will be immediately obvious to you whether the physical quantity you're looking at is invariant or is dependent on the coordinate system. And we like physical laws that are independent of the coordinate system that we'll talk about. So let's say the divergence of E is 4 pi rho. The divergence of E is an invariant. It doesn't really change. That expression doesn't change depending on the coordinate system that you choose. Unfortunately, that invariant depends on contravariant and covariant behavior, and I don't know if we'll get to it towards the end of the class, but just forgive me. We're writing for now everything with lower indices because there's what the book does. So that's that part. Then finally, I'm not a big fan of people learning math from random YouTube lectures. First of all, because sometimes the material is just not exactly what you're looking for. Sometimes the concepts are not put together in a pedagogically sound manner, but I want to make an exception. And one person that I think makes spectacular lectures, this is Pavel Greenfeld. He's in Drexel University. He also wrote a book. His lectures are fantastic. I've learned a lot about tensor calculus and about that. And he actually also makes that point very eloquently, saying that a lot of times people will rely on the underlying coordinate system to understand what certain operations are doing, but really we should try to let go of that. And that's actually one of the big points in tensor calculus. So that out of the way, let me see. Are there any questions before we can get to the math? So let's talk about some math. So we really should start with vectors, right? So like I was saying, we'll have to avoid the fact that we're doing everything in Cartesian coordinate systems for now, but just stick with it. So so vectors, right? So let's say we've got this vector A, and then we've got this vector B, and then if we would like to know what it amounts to when you add these together, you can say that this component, the ith component of that vector, translates to the ith component of the vector that comes out of the sum. So in other words, this is A sub I plus B sub I. right? So take two vectors, you can just add them together like that. It's also bilinear, which means that if you take some kind of a scale factor here, so this is, you do this times f, and then you do this thing times g, that term, that factor then rescales those components. So therefore, you'll find that so a f g b, and then that becomes a I g b I. Right. So it's easy to see these things. They rescale those vectors, and that's what we mean by bilinear, right? So it's the linear in both terms that enter into the sum. Now the length. So let's say the length of this vector a, you'll find it written in many ways. Sometimes like this, sometimes by single values. I happen to like this notation because it's the absolute value, and I like thinking about length as absolute value because it's a little bit like measuring the distance from this vector to origin, which is a little bit like doing absolute values on a one-dimensional coordinate system. But doesn't really matter. And if you have a vector's components, then what am I doing? Hang on. You can just square them, and then that's of course a, and there we go. You could square them, and then take the square root. So that's a generalization of Pythagoras theorem, obviously. And then there's the dot product. So if you have a vector a and you dot that with b, you are doing a projection of a on b, and depending on whether they're pointing in the same direction or there's some angle, that dot product is going to be rescaled by the angle between the two, right? So that's should be familiar. And then putting in b for a means that also we can write the length as the dot product of a with itself, and then take the square root. Okay, so that's what we can do. So that's the first product of two vectors. There's also the cross product. So let's say we have some vector c that we get by taking the cross product of two vectors b. What that means is, let me see if I can make a nice little drawing here. So let's say I got my vector a here, and got another vector b here, and then that's my vector c. Then the outcome of that cross product has a couple of important properties. First of all, that cross product, that vector c is perpendicular to both a and b. Or put it in another way, a and b define a plane, and c is the normal to that plane. And then, of course, the normal you could define as pointing up or pointing down, and we're using the right-hand rule, right? So go a to b. This should all be known. And then if you want to think about it this way, actually, the magnitude of that cross product is actually the surface area of this parallelogram. So that's the magnitude of c, or the magnitude of a crossed with b is the surface area of that plane that is spanned by a and b, or not spanned, a plane that is contained within a and b. Now, if there's some angle theta here, then the angle here is going to be a b, contributing to the outcome of that cross product, the length of that cross product, as going with the sign of the angle enclosed between a and b. So of course, I'm writing absolute value here, and this is a sign of theta. Then don't use negative angles, please, because of course now you're going to get length that is negative. But should be obvious that if you use positive angles here that are between 0 and 180, or 0 and pi, then that number is going to be positive. Important consequence is that if A and B are parallel or pointing in exactly the opposite direction, then that theta is either 0 or pi. That means the sine of that angle is going to give you 0. That means the length of that vector is 0. Now, that's actually very important, but it's also geometrically easy to see why that would have to be the case, right? Because if this A and this B, if they're pointing in the same direction, then the enclosed area is 0, right? And if they're pointing in the opposite direction, then the enclosed area is also 0. So because they're not really spanning a plane anymore, doesn't really have a surface area. The other way to look at that is that, of course, if A and B are not pointing in a different direction, you cannot define a normal to that plane. So it'd be kind of weird to say, okay, C must be pointing perpendicular to both A and B, because that would not be specifying a single vector either pointing up or pointing down. It would be defining a plane, and that doesn't work very well. So don't do that. So if you have these cross products, you can calculate the components. So there's Cx, it's A y B z minus A z by, and cyclically. What I mean by cyclically is that that means that you swap your x for a y, and your y for a z, and your z for an x, but you only go in this direction. Another way to look at the components of this cross product is to use this following. So these are your unit vectors. X crossed with y is z. And then whenever you have some kind of a cross product with A and B, you write it as components. So in unit vector form, A would be an AX times the x hat, and an AY times y hat, and an AZ times z hat. And then you distribute all the terms in your product, and then you use this rule and the cyclic permutation of this to figure out what that resulting cross product looks like. So what I mean by cyclic permutation here means, swap your x for a y, and your y for a z, and your z for an x. So that works. And then, of course, z, x, y. And of course, we also know that if we have A cross B and we swap them, got minus B cross A, you should have all the tools under your belt now to calculate actual cross products. Then there's a very famous triple product rule, which is, so this combines both the cross and the dot product. This is actually the volume of the, I don't know what the geometric name for it is, but let's say there's a B here, and then there's a C here, and there's an A here. So A, B, C. Then it's the volume that is in this three-dimensional object. It's a hyperparallelogram or something, I'm not sure. So that's the volume. That's this outcome of this product. So that's your triple product. And for triple products also you can use permutations. You can just swap your A for a B, B for a C, and a C for an A. So you can just get like B and then C crossed with A is C dotted with, this is C, A crossed with B. So that's all the same. That this turns out to be the volume is actually not that hard to understand, right? Because you have the outcome of that B crossed with C is a vector that's perpendicular to both B and C, which means it's pointing up. And if you dot that with itself, you basically are taking the surface area here, multiplying by that, and then therefore you get the volume. So it's not that hard to see why geometrically that would have to be the case. Then there are also triple cross product rules, and for that, you need to really be very careful about the order of where you put your parentheses. So for instance, this one, it's A dotted with C times B, and then minus the, let me see, that's A dot B times C hat. So this looks a little bit different, but of course, you know, you've got three vectors in cross product, so the right side needs to turn out to be a vector. So that works out because this is a scalar, so scalar times vector gives you a vector. This is scalar times vector gives you a vector. So left side is a vector and the right side is a vector. Okay, now Einstein notation. So what do we mean by Einstein notation? So first, let's go back to the dot product. It's most easy to see. So let's say we have A dotted with B. That means it's AX BX plus AY BY plus AZ BZ. This you can also write as the sum over I, where I is X, Y, and Z, or 1, 2, and 3, where you take AI times BI. Okay. Now, this should not look too weird. Now, but Einstein said, you know what? Anytime you see an index, like a sub index like this, repeat itself, we should assume that we're summing over it. So that means we can write this as AI times BI, and the sum is implied. So duplicate index implies sum over it. Oops, not sim, sum over it. So what does that look like? Well, let's give some other examples. So for instance, if you have this product, so you have an A dotted with B, and then you have a C dotted with D. If we write it without the sum notation, then A dotted with B means we are summing over A, so I, A times BI. And then we're doing the sum of over, let's say, J, C, J, D, J. And then you can actually write that as the sum over I and the sum over J of AI, BI, C, J, D, J. So it's two sums. And now Einstein notation says you could just write that as AI, BI, C, J, D, J. Okay, it's just shorter, and it should now be obvious that because we have a repeating index I, that means that's one sum, and we have a repeating index J, that's another sum. So that automatically says there are two sums here. If you've ever studied general relativity, you will have been very thankful that you will not have had to use these sums all the time. Okay. So that's Einstein notation. Let's talk about our first two-dimensional, if you want to think about it that way, geometric object with subscripts. So the Kronecker delta symbol, that is delta, and it's got two indices. So delta ij, and it's a very straightforward tensor symbol matrix. It's 1 if I is equal to j, and it is 0 if I is not equal to j. Therefore, you know, if you have a sum, so let's say we are doing a sum, and we have a sum over I, and then we also have a sum over j, and we're doing AI, bj, delta ij. Okay, then the sum over j means that only the terms that have a j equal to I, because it's multiplied by this delta function, not delta function, delta tensor. I use them interchangeably, sorry. Only those survive. So actually that becomes a, oops, the sum over I, and then that's AI BI. And now that's the dot product, right? So that's A dot B. Or in Einstein notation, it's like this. So A, J, oops, I started with an I. Let me start with an I to be consistent. AI, B, J, delta I, J is just A, I, B, I. There you go. That's your delta symbol. Okay, so for posterity, so the Levi-Civita symbol plays that role in the cross product, and has to be asymmetric under exchange of integers, and you can write it like this. All right. So that's the Levi-Civita symbol. Okay, now let's talk about derivatives. So if we have some kind of a function, and it is a function of time, then our traditional notation for taking the derivative is, let's say, ddt. We can just do ddt. We don't need partials because it's just one variable as the argument. It's going to be the limit of delta t going to 0 of t plus delta t minus ft over delta t. We can do the same thing. We could do the same thing with functions that are a function of vector coordinates. So, for instance, famously the scalar potential. So, for instance, if you have the scalar potential is a function of x, y, and z, for instance, in the Cartesian coordinate system. Then the derivative of this would be ddx. Now we should use partials. Where's my eraser go? Hang on a second. I butchered my eraser. I should really have a spare on hand. This is riveting TV, I know. Okay, so I should be using partials. You would do the same thing. You would say, well, that's the limit of some delta x going to 0 of our v x plus delta x minus v x over delta x. So that's the standard notation, and we could do that for one coordinate. We can also do this for time. It doesn't really matter. It's just the same way that we can do derivatives. Now this is usually not what you do when we're writing equations in this course. We will usually want to talk about not just the derivative in one direction. We also want to discuss the derivative in other directions. So oftentimes we'll use this operator. It's the Nabla operator or the del operator. It's this ddx, ddy, ddz operator. So, for instance, if we want to see how this thing operates on, let's say, some kind of a function f, then let's say we take the Nabla operator, we let it operate on this function f, and if f is a function of r, then that means we're going to get, even though this is a scalar function, because the Nabla operator gives you an x component that contains the partial derivative versus x, and the y component is going to be the partial derivative with respect to y. The z component is going to be the partial derivative of z. You're going to get a, instead of having the scalar field, you're going to get a vector field. So, for instance, you would get some kind of a new vector field that is probably still a function of R. So that's a scalar. We apply a vector operator on it, and therefore now we get a vector field. This is only in Cartesian. Another notation for this is to actually write this as follows: xi ddxi. So that's xi ddxi, which means that we're summing, right? So we're summing over this I and this I. So in other words, if we have this operator and we let it do this thing on our function f, what does that look like? You'll find that it's going to be written in unit vector form, right? Because, let me write that down. So if this is the Napa operator, that means we'll have xi ddxi of fr. So this is actually, I'm going to write this x ddx of f. I'm dropping the argument, plus y ddy of f plus z ddz of f. Right, so this is again using the Einstein notation. There's an even shorter notation for this, and that is you can write this like xi di. So that di is just one of the partials, and that di is or del I is the shorthand version of this. So write out in Einstein form this product. All right. So so we just follow the we just follow the procedure. So we have our Napa operator or del operator. It's I'm going to write it in several forms because they're all fine. So that's xi ddx of I, right? So, and now we're dotting that with the v. That means that we need to write v in index notation. So v would be v I x I. And now this is they're still dot products. So this makes it a little bit hard to read because we're kind of mixing our notations here, right? So, but fortunately, the xi and the xi, the dot product is 1 anyway. So we actually get d dxi vi or di vi. Now, I actually like this form way better than this because it's way more compact, right? Isn't that nice? Yeah, it's really sweet. So this is this of course is the divergence. And before, when we were taking the Nabla operating on a scalar field, we call that the gradient. So this is the gradient. All right, so let's take until, let's see, O2. So so that's let me see. So we've done divergence, so div, we've done grad, and now curl, right? So the curl is like this, right? So it's the cross product of the Nabla operator with v, and then you can actually write that in component forms as a let me see, epsilon I, j, k, and then we're taking our del of j, and we're taking the vector v as k. Okay, so that's the ith component of the curl, and then if you actually want to write it as a full vector, you can do what Jocelyn was suggesting. We can do that. Okay, then you just get d, j, v, k, and then x hat I. Done. All right, so that's the component form of the curl. Okay, now there are higher order derivatives as well. Right, so there are many. The most famous one is actually this one, the Laplace squared. That's the Laplacian. So that's actually the Laplacian. That is in there's a shorthand operator for it, which is this one. This is in Cartesian form. For instance, it's the ddx squared plus ddy squared plus dz squared, right? Because you're taking the dot product of the Nabla operator with itself. So it's a little bit like taking the magnitude of the Nabla operator. So the magnitude squared, because we didn't take the square root. So that's what it would look like. Or if you want to look at it this way, it's actually di di. So that's the Einstein notation version of this, which is shorter. And actually, if you want to be careful with contravariant, covariant, one of these has to be contra, the other has to be covariant. So, but that's okay. So this is actually the so that's an Laplacian, and then you can also think about it as the divergence of the gradient, if you want to think about it that way. So, for instance, if you do this, it's the same as the divergence of the gradient of f, right? So this makes it into a into a vector field. So this scalar field becomes a vector field, and you dot that with another vector operator, and then out comes a scalar again. So even though this looks like it's a vector, but because I like putting the vector here, finally, because it's a vector operator dotted with itself, the outcome is actually a scalar, and that's why this Laplacian symbol actually is a nice operator to use as a shorthand for it, because it makes it explicitly clear that the outcome's a scalar. All right. So there are more higher order derivatives. I want to make a point about this thing called the Helmholtz decomposition. There is this statement, decomposition, I should talk and write. So Helmholtz decomposition, that says that any vector field you can decompose in two parts, a divergence part. So let's say you have some kind of a field, F, you can write that as a the gradient of some what was it going to do? I think I was going to do phi, but yeah, let's do phi. Plus the curl of some kind of a other vector field. And the statement is that you can do this for any vector field, which means that once you have a vector field that looks like the gradient of something, afterwards, if you take the curl of it, it's not going to exist anymore, because you already took the curl out, because you started with something that had the gradient as its only component. Similarly, if you have something that is only built by taking the curl of a vector field, afterwards, if you want to take the divergence, you're not going to get anything. So, or written in a different manner. So if you take the curl of something that is the gradient of f, you're going to get 0. And also, if you take the divergence of something that is the curl of some vector field A, you're also going to get 0, right? Because this vector field is already completely divergenceless. Divergenceless. So this term is then sometimes called the rotation, and this is then the divergence part. It's a wonderful way to think about final one that I want to mention, because we ran into it on Monday, is this one. So it's the curl of the curl, right? So that is actually, it's the gradient of the divergence of that field minus the Laplace squared, or rather the Laplacians of that vector. Now, again, be careful. This, even though this, it's the Laplace operator squared, so the operator itself is scalar. So it's a scalar operator, it's a differential operator, but it's operating on a vector field. So out still comes a vector field. So even if you write this as Laplacian, so you're going to write this like this, this is still going to be a vector field, right? Because you're doing a scalar operator, second order derivative on this thing. Same thing here, right? So the divergence of this vector field A is going to give you a scalar field, and now you're taking the gradient of a scalar field. Again, you have a vector field. So this is a vector field, and that's a vector field. And then everything is copacetic. So integrals. So we know that we know that we will find many types of integrals. So the first is, of course, the line integral that says that if you have some kind of a vector field, let's call it the vector field V, and or scalar field something, so something, and then we're integrating that over the line. That could be a DL, and so L being a line segment. So we could take, of course, line integrals through vector fields. We could take line integrals through scalar fields. So for instance, there could be a version that looks like this. So V DL. Now note that I didn't put a dot here. So out will come some kind of a line integral through a vector field. So there is going to be some kind of a vector field that comes out. But this famously is, of course, scalar, right? Because this, even under the integral, when we're writing this dot product, that's already a scalar thing. It's an infinitesimal scalar thing, but we're integrating it. So, the integral over scalar is still a scalar. Okay, so that's these are your line integrals. Now, let's see, one dimension up. So we'll do surface integrals. All right, so surface. Oops. Now, the book is suggesting that we use this shorthand, so just S ds, and then something that we're integrating over. It's sometimes useful to explicitly write things that are two-dimensional as a double integral, because you're integrating over a surface. However, as soon as you do this, then you should also start splitting this up. Let's say there's a ds1 and a ds2, or you could write this as a d squared s. So then it's clear that you're doing two integrals, even though in the end, for instance, if you end up integrating over solid angle, you could still do it in one go. But it's good that to make it explicit that this is a surface integral, because sometimes that's lost if you just write the single integral, and then if you have if you just have ds, your only indication that you're dealing with a surface integral is the fact that we've used the symbol s, and I think that's not explicit enough. Now, of course, you will not find these things out in the wild without any context. So hopefully you'll be able to find, people don't tag train stations with this stuff. So hopefully you'll have enough context to determine whether you're talking about an actual surface integral or something else. Okay, so surface integral. Let me see, volume, yes. Okay, so volume integral. All right, so volume integral, so that's it, be triple integral, something, and then d cubed x. That's how the book likes to write it. There's a shorthand of something dv, where v is the volume. So those are the types of integrals that you will find. I don't think we'll do more. I don't think we'll do more than 3 triple integrals. I don't think we'll do quadruple. Oh no, actually we will. We will do quadruple integrals for Fourier transforms. Okay, we'll do k and t. Okay, so these are just your notation things. Okay, so let's talk about Stokes. So Stokes says that so if you have some vector field and you take the curl of that, and then you dot that such that it becomes a line integral. So this is a line integral. Then that is the same. Sorry, that's a surface integral. My eraser is not very clean. Yes. So this is a surface integral, and that is equal to a line integral of v dl. Okay, now this is one of those things where it's useful to be explicit about the number of things that you're integrating over. So for instance, you could write this as d squared s, or you could do something like this. The other thing we're doing is that this line integral is the edge of this surface. So that's this surface, and that surface is circumscribed by this contour. So this is the edge of S. So let me draw that for you. So some kind of a weird surface. This is the edge or contour. It's del S. We reuse the symbol del again. Okay, so this is our surface S. And that's our surface S. So we have some kind of a vector field, and if we're integrating that over the surface area, then the sign that comes out is given by the right-hand notation. So that looks a little weird right now, but we'll encounter examples where that's important. But so right-hand notation meaning that if you're integrating in this direction, so using your right-hand rule, so the sense of integration is this way. That means that this is the normal that your surface integral is going to be referring to. So famously, this convention is used in Ampere's law, right? So, or Ampere-Maxwell's law, right? So you have a contour integral over some edge, and that's where you evaluate the magnetic field, and then your thumb is indicating the direction in which the current is flowing. So these two are not only linked by the fact that this is the edge of that, there's also a sign convention given by this is going in one direction, and then therefore the sign of this integral is related to that by the right-hand rule. So finally, we like putting this circle through it because it's a line integral and it's closed. And it's a closed line integral because you have a surface, and if you have a surface that's well defined, of course you can always describe what the edge is, and you have to do the integral over the complete edge. I forgot if there are weird cases where you can split the edge up in two parts, but I usually don't see Stokes being used without this. So we just say this is the complete integral over the edge, and then their sign convention is their right-hand rule, right? Is the right-hand rule. All right, so that's Stokes. Gauss, which I mistakenly called green. So we have some kind of a volume integral. So let me write it explicitly for now. And it's the volume integral of the divergence of something. So, and then it's a d3x. And then Gauss says that that is equal to a surface integral of that same vector field, but dotted with the normal of that surface. Okay, so what are we looking at here? In this case, we're talking about some kind of a volume. So this is volume, this is 3D. Then the normal is pointing out. This is one of those sections ds. So it's an infinitesimal patch ds, and we're integrating over all of those. And then the normal is pointing out. Now, the only reason we can define the normal pointing out is because this 3D object, it's closed, it's got no holes, so we can unambiguously ascribe an inside and an outside. So therefore, we can say this is pointing out. And again, for this is the edge of that volume. So this surface, we have to do the integral over the entire surface, and this would be the edge of the volume. So that's the volume. That's the volume. And the sign convention is here that n points out of the volume. Okay, so so the shorthand version of this is, which is the one that I used before, the V or D3X is V D S vector. All right, so then the S vector is shorthand for this. And we don't write the triple integrals, and we usually drop this circle through it. But this should be instantly recognizable as the Gauss's theorem. Okay. So last one. Fourier transforms. So I have a quiz for you guys. So let's say I have a differential equation. So x dot dot plus yeah, let's call it x is some f of t, and this is a general. Let me write it as a general expression. So it's a 1D problem, it's not complicated. But the complication lies in the fact that we have an arbitrary force. So the question is, how do you find and I'm going to let you think about that for a little bit. Of course, the subject is Fourier transform, so you should be able to figure out how that works. All right, so the tricky part about this is the fact that this one's arbitrary. So if this was a sine wave, let's say, so d is some sine omega t, sorry, f is some f naught sine omega t, then you could just say like, well, you know what, let's just be real. And, you know, if this thing is sinusoidal, there's really no need for these things to be anything other than sinusoidal. So you could just try it, right? And then you can do your, you know, find the most general sum of all the possible solutions and then add them up together, figure out what the boundary conditions are, et cetera, et cetera, et cetera. Okay, that's fine. That's the classic ODE situation, right? But actually, using Fourier analysis is really nice. So what you need is the following. You need to know that if you take the Fourier transform of some function of x, then and let's call that big X, big X omega, then the Fourier transform of the first derivative is I omega X omega. And if you do it another time, anytime you take a derivative, you throw in an I omega. If you do Laplace transforms, you pick up an S, okay? It's the same thing. So you can take the Fourier transform of this entire expression, and then you'll get minus omega squared times m times big X of omega plus k times big X of omega plus whatever the Fourier transform of f is. And we don't know what it is because it was arbitrary. So we could just say it's f of omega, okay? And now you've reduced the problem from a differential equation problem to a polynomial. And now you can just factor out your x. So here's your x. That is your f of omega over k minus m omega squared. And now all you need to do is take the inverse transform. So your x of t is the inverse transform of this side. And then you're done. So there's one more step to this. So this is actually the product of it's the product of two functions, and the Fourier transform of the product of two functions is the same as the convolution of the functions in real space. So if you really want to, you could write this as a convolution integral where you say, I'm going to call this by definition 1 over g, and then this is going to be the convolution of g convolved with whatever f of t is. And then this is actually the real space form of the Green's function, which is the natural response of the oscillator. Anyway, the rest is just executing the integrals. But the nice thing is that it's a one-way recipe. It's not, doesn't really take anything more than that. All right. So that concludes by default our lecture. Made it halfway through Fourier transforms. I wanted to do a couple of the Fourier transforms and then delta functions, but they're not a lot of work, so we can probably keep going. So I think we're good on schedule. So that's all I had. Like I said, my office hours, I'll hang in there as long as you want. But if you do have questions for office hours, I ask that you stay on now and that you don't call in at 7:44 with 100,000 questions.